Hello, my name is Aiym Tleuova, and today I will be talking about temperature-responsive, safer formulations of fungicide. I work at the Department of Chemical Engineering under the ChemJust project. The annual crop losses due to plant disease and pests are estimated worldwide to account for 20–40% of total crop production. Among diseases, fungi account around 40%. Only in 2006, 16% of the global harvest was damaged because of microbial disease, where 80% of these losses were caused by fungi. As such, fungal infections cause substantial food and economic losses, especially in developing countries, which are additionally plagued by climatic extremities and domestic conflicts. Fungicide, a specific type of pesticides that inhibit or kill the fungi. They have been widely employed in order to prevent or reduce fungi-related crop damage and increase the efficiency of agricultural production. According to EU pesticides database, among 496 approved active substances, 147 belong to the category of fungicides, which is around 30%. Yet they account for 46% of all the pesticides sold in European Union. As such, agricultural industry is heavily relying on the use of fungicides, with an increasing trend emerging. Introduction of synthetic chemical pesticides in 20th century have effectively controlled pests and led to yield significant increase. These are numerous advantages of using plant protection products, such as increase of yield, which leads to increase of amount of fresh vegetables and fruits in the diet, and that contributed to the improvement of public health. However, as with most pesticides, fungicides can be harmful to the environment and human health due to their acute or chronic exposure resulting from direct or environmental transfer. Less than 0.1% of pesticides applied for the pest control reach their target pests, and the rest, 99.9%, move into environment. Many pesticides contain active ingredients that can cause environmental pollution in the atmosphere, soil, water, and other environments when runoff occurs. For example, through drainage water or losses through the wind when applying by spraying. Pesticides runoff can lead not only to the environmental pollution, but also to plant protection products losses that lead to the efficiency reduction and economical losses as well. Therefore, we can highlight the main issues, which are the toxicity to environment, professional health problems of workers who are involved in the field works, and population living in the vicinity of application, low efficiency of these pesticides as well. Nevertheless, pesticides remain the main and the most efficient way to fight with plant diseases, with demand for fungicides use remaining high. Therefore, the development of new approaches to reduce their side effects and move their performance is urgent. Microencapsulation is a widely used technique to store active ingredients that either need to be protected against degradation caused by aggressive environment, or vice versa, to protect the environment, for instance, to avoid allergic reaction and professional health problems of workers in the industry, to reduce an ecological burden to nature. Another advantage of microencapsulation is that it also allows delivering small amounts of active ingredient along with controlled release and targeted delivery, enhancing permeability, stability, and solubility. Therefore, studies on sustainable use of pesticides to reduce the risk of their use on human health and the environment are of great interest of researchers. And the number of publications is growing steadily each year. You can see it in the figure from the right side on the example of fungicides. In the last 24 years, the increase in the number of publications focusing on the general topic of fungicides increased linearly, and the growth of interest in the controlled release has been growing exponentially. There are different environmental factors affecting the growth of fungal pathogens, such as temperature, pH, oxygen, water availability, and light. The ideal condition for the majority of fungi growth is in a range of temperatures between 25 and 30 Celsius degree and relative humidity of 95%. In the frame of ChemJ's project, I used widely used pyraclostrobin fungicide to create microcapsules, releasing the fungicide only at certain conditions. In general, microcapsules can be designed in the way that they can have different modes of release. The release can be slow and continuous, as it is shown in the capsule or pictures from the left side. You can see that. Otherwise, release can be triggered by some specific factor. It can be light, magnetism, pH, temperature, and so on. Such capsules found a wide application in different fields, including agriculture. In order to design temperature-responsive microcapsules, phase change material was used as a core of the capsule. Phase change materials are substances that can absorb and release thermal energy during the process of melting and freezing. And here, the use of phase change material affects the diffusion rate of fungicide. For example, when melting, the release rate increases, and when freezing, it captures fungicide inside and does not allow to diffuse through the walls of capsule. The average size of obtained microcapsules was of 200-600 nanometers, with the presence of bigger capsules with a diameter of 1 to 4 micrometers. Here you can see scanning electron microscope pictures of microcapsules with different amount of pyraclostrobin inside the oil phase, which is octadecane. It appears that increasing the amount of pyraclostrobin in oil phase leads to the appearance of bigger capsules. To prove the successful encapsulation of pyraclostrobin inside of these capsules, Fourier transform infrared analysis, TGA analysis, and HPLC was used. Here you can see FTIR curves, and for example, the peak at 1547 and peak of 937 were characterizing pyraclostrobin encapsulated in the capsules, and this peak at 1547 is associated with stretching vibration of the benzene ring skeleton of pyraclostrobin molecule, which you cannot see in the blank capsules. And the same with the peak of 937, which corresponds to absorption of CN stretching vibration, which can be found in the spectra of pyraclostrobin microcapsules, but not in the blank. TGA analysis also confirmed the chemical composition of obtained submicrocapsules. However, I will not discuss it deeply. But interesting point here is the findings from DSC, that these results showed that the microcapsules containing more phase change material demonstrate better thermal activity of capsules. The antifungal activity tests of pyrrolobenzene-loaded microcapsules at temperatures above melting point of octadecane, which is phase change material, and below it, showed that at 25 Celsius degrees, pyrrolobenzene submicrocapsules did not have any antifungal activity effect, but at 35 Celsius degrees showed luxuriant growth of fungi. No antifungal effect can be observed below because below the melting point of octadecane, the pyrrolobenzene almost does not diffuse from the oil phase. The blank submicrocapsules do not show any zone of inhibition at both 25 and 35 Celsius degree. This clearly indicates that silicon nanoparticles, octadecane, does not exhibit any effect on the fungal growth. Submicrocapsules loaded with 5 and 10% pyrrolobenzene exhibited a good antifungal activity and have potential to inhibit the growth of fungi incubated at 35 Celsius degrees. The antifungal activity results evidently show that the submicrocapsules work on the basis of thermal response release. The environmental responsibility is important in the same way as performance efficiency of fungicides formulations. Therefore, cytotoxicity tests were conducted to study the toxicity of obtained capsules. Cytotoxicity test toward Artemia salina naupli, that is brine shrimps, demonstrated that the positive control of technical grade pyrrolobenzene shows the highest toxicity value in this test. In overall, pyrrolobenzene submicrocapsules containing 5% of pyrrolobenzene showed 29 times less cytotoxicity than pyrrolobenzene technical grade. It was noticed that pyrrolobenzene submicrocapsules cytotoxicity depend in direct ratio on concentration of pyrrolobenzene. The octadecane concentration also affects the cytotoxicity of capsules, as octadecane concentration lower, the more cytotoxicity of the capsules. So cytotoxicity effect of concentration of octadecane can be explained by the state of octadecane in the core of capsule. The tests were conducted below the temperatures, below melting point of octadecane, and therefore high amount of octadecane can entrap more pyrrolobenzene and does not let it to diffuse through the shell of submicrocapsules. Therefore, we can conclude that developed capsules of pyrrolobenzene can be used as safer alternative to the conventional fungicides. More on this topic you can read in our review article about current state of new formulations of fungicides published in Journal of Controlled Release. Thank you for your attention. Bye.